Hello everyone, welcome back to the series on programming robot mechanics. In this video, we are going to implement the robot Jacobian. Now one would say we had already calculated the Jacobian in the Newton method. Well, this is particularly kind of similar concept, but a different thing. This time we are going to calculate a Jacobian matrix for the robot inside the robot class. Now, what is a Jacobian? Jacobian of a robot. A Jacobian of a robot is this matrix that actually translates, or we can say transforms, the joint or the parameter velocities to the Cartesian velocities. Cartesian velocities in the sense of x, y, z and their respective rotational velocities as well. So this transformation is accomplished by a Jacobian matrix. Now this is really useful. This also helps us when we are solving the dynamics of the robots as well. Kinematics is actually useful. We can see that it transforms the velocity. Now, a really cool example would be that if we want the robot to move in a straight line, like horizontally, then we can use the Jacobian matrix to compute what should be the joint velocities in order to achieve that goal. Right. Right. Okay. So the Jacobian matrix is actually calculated by this very simple formula, which we are going to code in this video going on. For the revolute joints, the formula is given something like this. R0 I minus 1 is actually the rotation matrix starting from the base frame till the I minus 1th frame. Similarly, D and R0 I minus 1 over here and over here as well. For prismatic joints, it's really easy, but for revolute joints, we actually need to calculate the cross product. This will actually be handled by the NumPy module that we will be using. And this D0n is actually the translation vector, like starting from the base to the end, like the last frame that we have, the end effector frame. And D0 I minus 1 is actually from 0 till the I minus 1 frame. That's how we're going to compute. So all these calculations are going to involve the transformation matrices that we are going to multiply and finally get from 0 till I minus 1. MATLAB also provides us with the implementation by the name of geometric Jacobian. This one, geometric Jacobian, which actually takes in robot, the configuration and the end effector name. We are going to have something similar like this in our robot class. So let's get with this. We're going to use the formula that has been described over here. So let's do this. Okay, so we are in the robot class and we are going to add this function towards the end. Not exactly towards the end, but after inverse kinematics. So let's do this. We can name this get Jacobian. Yeah, we are going to name get Jacobian. And we're going to have parameters self and the configuration that we have, something like the forward kinematics Q. And we are also going to take the end effector name. Now there are two ways to go about doing this. Either we can give the user the flexibility to allow him or her to select which end effector he wants, or like which link he wants to set the velocity of, or we can simply calculate that for the end effector. I think we should go for the end effector one, because most of the time x dot, y dot, or x velocity, y velocity, they are mostly presented for the end effector that the robot has to follow. So let's not include that. Simply let's put Q over here. Now let's add some documentation. So one thing that we need to note is that the Jacobian is calculated for each particular configuration of the robot. So if a robot is at, say, a home position, then its Jacobian will be different for, let's say, the robot is at an goal position or something like that. So for each set of transformation parameters or the joint angles, if we were to say, we are going to get a different Jacobian for all these cases. Right, now let's start with this. The first thing that we need to do is to get the rotation matrices or the transformation matrices starting from 0 till the degree of freedom frame. So let's do that. And then we will extract all these values one by one. So first of all, let's have a list of transformations. And we are going to do something similar to what we have already done for the forward kinematics, or we can say this one over here. Something similar to the transform function, like we are going to loop over all the transformations and keep appending them to one of our transformations list that we have. Okay, let's do that. And okay. So the first parameter that we should have is np.i 4. This is the base frame that we have, and we are going to run this loop till the end, like the total length of the links. And this is going to transform. Yeah, so we get the transformation and we are going to append that. Okay. One thing that we need to do is, okay, let's structure it this way. Or we can do something like this. Okay, now we are in the initial part. We have this base frame that is actually the identity frame that we have, and then we are looping over all the all the links one by one, and we are calculating the transformation, the homogeneous transformation for each individual link starting from 0 1 base to 0, or we can say 0 to 0, 0 to 1, 0 to 2, 0 to 3, something like that. And that way we are going to append every transformation that we have. Now we have a list of transformations that is a very big list. And now we are going to generate the Jacobian matrix. So let's see how we do this. So first of all, we know that the Jacobian is going to be the shape of the Jacobian matrix, how it's going to look like. It's going to be 6 cross degree of freedom type of matrix. The shape is something like that. And now let's see how we will do this. So the first thing that we need is the end effector D. So let's right, let's name it this. So this is going to equal transformations, the last that we have, and then we need to sub-select some of these values. Now, what translation end effector is actually the last column and the first 3 rows. Okay, so we are going to select the first 3 rows and the last column, that is going to be -1. Or we can add 3 over here, that will be more interpretable. Okay, so for the next part, we actually need to calculate this matrix multiplication or cross. This matrix multiplication over here and this one as well, R0 I -1. What this actually means is this function, that multiplication, can easily be reduced to something like now this is the multiplication that they have given, but actually what this implies is what we have to calculate. If we are given a matrix something like this, 0 0 1 0 0 0 1 0 2. So if we have a transformation matrix something like this, what that multiplication does, it will actually get us this 3 vector, like which is this first, second, third column and these first 3 rows. It actually gets us this, and then we cross product this with the translation end effector minus the part that they have written over there. We can directly compute this, and we are directly going to compute this, avoiding that matrix multiplication that they have given us. Okay, let's add a loop for that. Now we are actually looping 2 times. A better way would be to, since we are also using transformation as well, a better way would be to combine both of these. But all right, we will combine these towards the end of the video. But first, let's try to just get a general idea of how the computations are going to look like. Okay, first we're going to get the transformation, that is going to be transformations I that we have. And now we are going to get the rotation vector that we have, that we want. Or we can simply remove that. Then we have this. Okay. 3, 0, 1, 2, 3. Right. 2. So 2 is the one. Like 3 is the last one, 2 is the second last one. That is what we get. And we have this translation end effector and rotation vector. So let's calculate translation vector. This is also going to be almost equal. So now we have these two values that we wanted. Now we're simply going to compute whatever computations we want to do on this. Okay. So we're going to go to the Jacobian and the ith column, row cross column. That's how we do it. So ith column, we're going to select that. And we are going to calculate the first 3 elements. The first 3 elements are actually equal to np dot cross. And we take in the cross as first the rotation vector. And then we take in the translation end effector minus translation vector. Okay. And the next 3, we are going to compute them in some way like this. Let's add some space. And they are simply going to equal the rotation vector. Now, one thing, this is only for the revolute joints. For the prismatic joints, this cross product will not be present over there. Simply the rotation vector and 0, 0, 0. Okay, now let's add this over here. If dot links I. Okay, we need to just consult the links part that we have. And the link actually has this joint type that is going to help us. Let's close this. Now, if the joint type is equal to revolute, then we are fine with this. Otherwise, we need to do something else over here. Now, that is simply going to equal the rotation vector and a zeros vector. Just a 3 size zeros, or we can simply ignore it, but or let's add this for the sake of readability. Otherwise, we would forget like why we didn't do anything. So just for the readability part, nothing more than that. Okay. Now this is one thing that we have done. What else we can do? Now let's just merge these 2 for loops, because running them again is kind of looking redundant. But readability wise, these look good. So let's do that. So we are going to cut this out, and we do not require this transformations as well. So we're going to remove this overall. Okay, let's just name this transformation, and transformations I is not required for this. Okay, transformations dot append. Okay, now this thing can create a problem because we will not be running through that. Okay, right. Okay, so the problem with this merging is we won't be able to get the translation end effector all out like that. So I think it is better to just have the 2 for loops for now. Like in order to calculate this translation end effector variable, we actually need transformations, the last transformation. So we are going to calculate this finally. So why not calculate it over here as well? That would be all right. Okay, so this computation is done, and then we can return the Jacobian that we have. All right. Okay, no mistakes as such that I can see, but the tests are going to tell what mistakes that we made. So let's get on with the tests now. Right. Now we're going to add this test in the test robot file, and I'll just fast forward the test while we create it, and then we'll see how the results come out. All right, one thing I noticed, why not we name it to get calculate Jacobian instead of get Jacobian? Get Jacobian seems like a little too, like we have already calculated Jacobian and we're trying to get the Jacobian. Calculate Jacobian really feels like that we are actually calculating the Jacobian in real time. So we're going to change the names over here. Okay. And now we are going to create this same robot that we did in the previous videos as well, and then calculate the Jacobian. So let's do that. Okay, so this is the value that we have. Now let's check if we are also outputting the same value or not by printing this Jacobian matrix. Now, one thing to note, why these values are actually different. How we are computing the Jacobian is slightly different from how they are, how we are representing the Jacobian is actually different from how they are representing the Jacobian. This is something like their Jacobian is actually calculated in this way: omega x, omega y, omega z, vx via vz. For the guide that we are following, the formula that we are following, we are calculating the velocity Jacobian first and then the omega Jacobian. Right. X dot, y dot, z dot, omega x, omega y, omega z. Now, one strategy would be to inverse these two values, like whatever is over here, we put it above, and whatever is over here, we put it above. So let's try and see how the values change if we do that change. Okay. Okay. Okay, so running the test seems like we are getting some form of error over here. Now, I have actually debugged where the error is. So let's just try to understand where the error came at the first place. Now, this Jacobian matrix does not actually equate to the Jacobian matrix that is over here. Let's calculate it again. To this Jacobian matrix over here, like some values are kind of off. So the problem for this thing is, it's actually the problem on our side. What we are doing, are now this is a problem that we have, similar to a problem that we have faced before as well. So we need to deal with this and keep in mind that our framework is something like that. The transformations that we start is actually the np.i4. What this does, it creates the transformations list, actually a degree of freedom plus one kind of a list. So this np.i, this is not actually to be counted as a frame, as in the frame counting should actually be started from the transformations that we have computed over here, like starting from the first index. Now, in order to solve that, that is a very easy fix. We can add I plus 1 over here. So that was the thing that was missing, and that's why it was computing and giving us the wrong results. Now let's try this again. I've saved that. And let's try this again now. Now we can see that the values are pretty much the same that we are getting over there. Yeah, right. Okay, so that was a simple problem. Now we have faced this problem a while back as well when we were, I think, calculating the forward kinematics. In that, we were taking like Qi and np.i4. Now we need to keep in mind that this np.i4, the identity matrix, should not be counted as a frame of the robot. It is actually just a reference that we use in order to start the calculations, and that's it. The actual frames that we should be starting with are the link 0 ones. So that was the slight problem. Now all is left is to just add this np.testing part. So let's do that. All right, so our tests are running fine, and it does seem that everything is working fine. Now, there might be certain doubt because we are using 0.1, as we discussed in the previous videos, that this unit test is kind of not up to the mark, that we can say. All right, so I think this is pretty much it for this video, and this video also marks the end of the yes, I think this video also marks the end of the robot kinematic stuff. Everything that is related to position and velocity, where like everything that just is the motion, but not considering the cause of the motion. From the next, not the next, but from the next to next video, we are going to start with the dynamics part as well. In the next video, we are actually going to start improving these unit tests and also write some documentation for this library that we have developed till date. So we are up to date with all the tasks. And we are going to improve these tests in those, like we might face some new errors over there, but we'll see how we get along with all these. And then we're going to start with the dynamics part. So, right. All right, then. See you in the next video then. Bye.